All right, this is Mr. McMurray, and we're going to talk about the solar system today. And we'll talk about stars and a little bit about out in space also as well, but we only have one week, so we probably won't be able to talk about the whole universe all at once, but we'll get at least a big part of it. Okay, I start with solar system, and specifically our solar system. There are other solar systems. Uh, Solar meaning sun. It's a system of objects that rotate or revolve or orbit around a sun, and they're bound by the gravity of the sun or other star, and it includes planets, asteroids, dwarf planets, the moons around the planets, and maybe some other comets and other objects associated with that. And so that whole area is the solar system. Now, this is a picture of the solar system. Actually, not a picture, but a depiction of the solar system. Now, to be honest, first of all, there is no such thing as a scale model of the solar system, and you will never see a solar scale model. All right, because the sun is so humongous that in order to show it at a size, these other ones are very small. Even now, this one is on scale to size. If this is the sun, there's Mercury, Venus, Earth with its moon, Mars, Jupiter, Saturn, Uranus, just for the record, it's called Uranus, not Uranus. But anyhow, and finally Neptune out here. And at one time there used to be a little Pluto spot down here at the bottom, but it's not there anymore. Now, why will you never see a scale model? Well, basically, in order to show them either if you made them big enough, you could actually see, say, the Earth, for example, or Mercury here. The sun would have to be so large, and they have to be so far apart by distance you would not be able to see them. Okay, they'd be spread out so far, it'd be miles and miles and miles, and you wouldn't be able to see them. Okay, by which I want to emphasize the point is there's a lot of empty space in the universe. If you just pointed a rocket ship and just shot it off into space, the odds are you're not going to hit anything in the solar system and even outside the solar system. Okay, so you have to really work at it to actually hit even the moon, which is fairly close to us, relatively speaking. Okay, so or if it were, say, to be controlled within this room, the pieces, some of the pieces would be so small that you would not be able to see them. So you can't keep it on a scale model. Okay, so just keep in mind any picture you see of the solar system is not 100% according to scale. Now, this one, I think they have tried to keep the size of the planets in proportion to each other and to the sun, but obviously they couldn't even show you the whole sun there. And once again, the distances are not anywhere near close. They would be extremely farther apart than this shows. So, for example, if the sun were a tennis ball, okay, the inner planets, which would be Mercury through Mars here, would be the size of a grain of sand, and they would be within the first 30 feet away from. So you would have a tennis ball, then you would have, within the next 30 feet, you would have 4 grains of sand. Okay, Jupiter would be a size of a pea, like a green pea, and it would be 75 feet away, almost twice as far away. All right, already 75 feet is 3 rooms away. Okay, so and then Saturn would be an even smaller pea, but it would be 3 times as far as Jupiter. So it would be 200 feet. Okay, that's 2/3 of a football field away. Okay, Uranus would be a BB, just a little tiny metal BB. Okay, and it would be 400 feet away, which would be a football field and a third, so 130 yards, okay, away. And Neptune would finally be another BB, and it would be 640 feet, which is over 2 football fields away. Okay, now if they were literally that far apart, stretched, you wouldn't be seeing the grain of sand. You probably wouldn't be seeing the BBs or the Ps for that matter. You see the tennis ball maybe, but maybe not. Okay, so you can see how relatively far everything is and away from each other. Okay, not any danger of any of these planets running into each other or anything like that. Okay, so basically the point is the solar system is full of a lot of empty space. Okay, real quickly, just to summarize though, these first 4 are called the inner planets, Mercury through Mars. They are also called sometimes the terrestrial because they're more like Earth, and they're also called the rocky planets because they tend to be of solid rocky cores on them. Okay, then you have the outer planets, Jupiter through Neptune, and these planets are called the gaseous giants because they're made primarily of hydrogen and helium, but they also have ammonia and some other gases and so forth, rather than being mostly solid rocky. Now, some of those gases may be under such pressures that they may be liquids or even solids, but they're mostly what we would consider gas, and therefore they're called the gaseous planets. Okay. Now, another thing to consider is distance. When we're talking about the solar system, we usually measure what we call astronomical units. Okay, and an astronomical unit is the distance from the Earth to the Sun. Okay, and that is, just for the record, 150 million kilometers, which would be about 75 million miles, give or take a little bit. Okay, so it's a long way. All right, so obviously then planets like Mercury and Venus would be less than one astronomical unit away, and ones that are farther will be more than one astronomical unit away. Now, once we get outside the solar system, then we start measuring things in light years, which is the distance that light can travel in a whole year, which is also very big. But we won't worry about that right now. Within the solar system, we use astronomical units, comparing things to how far they are uh, from the sun compared to how far we are, because obviously the world revolves around Earth. All right, now let's talk about where the solar system began. Obviously, no one was there. We think it happened about 5 billion years ago. So, obviously, some of this is theoretical. Just like a lot of we're studying space, things are far away and difficult to test hands on, and things that took a lot of time. So, it's hard for us to say exactly what happened. But this is based on the best information we have. But obviously, keep in mind, it's not as certain as things that would be on this Earth that we can planet test and whatever like that. But the idea is that originally the Earth became formed, the solar system, Earth included, formed from a nebula. Well, where did the nebula come from? Well, possibly the remnants of a previous star that had blown up into pieces. Okay, once again, obviously, we don't know a lot about that. We think that this is the nebular theory, and the nebular theory is there was this nebula in space. Now, the items in the nebula just means cloud, by the way. Looks like this cloud of stuff. Okay, as uh, kind of started pulling together gravity. Any two objects exert a gravitational pull on each other. So these objects started pulling together, okay? And the closer they got, we know the force of gravity gets stronger as the distance decreases. So they started pulling together, and probably originally somewhat of a blob. Now, they also began to rotate or spin. As it spins, kind of like if you had a ball of dough and you start spinning it around your finger. I never could do that. It looked really cool when they did it in the Italian pizzeria or somewhere. But anyhow, it would flatten out. And so as it spun and gravity got stronger and stronger, faster and faster, it would also begin to flatten out. Even the Earth is slightly flattened at the poles because of the spin of the Earth on its axis. Okay, so same kind of thing. It started to flatten out. Now, as it did so, and gravity's pulling on it, gravity is strongest in the middle of this cloud, okay, and therefore you have the highest temperatures. It's pulling these things, forcing them together, and it's creating heat. Okay, in the very center of it, we would have a proto sun. Proto sun, that just means a before the sun, or the beginnings of the sun, and it was just a mass of gas and solids and so forth. They're being pulled together at these very high temperatures. Okay, it would also get fairly hot close to it, and as you get farther out, it would be less hot. Okay, and so basically over time, the center collapsed into a big enough space and created enough heat that you had thermonuclear fusion. We talked about fusion before. Fusion, and once that ignites, then that becomes the sun. Okay, now farther out from that, it began to coalesce, anyhow, group together in little clumps, and you would have Mercury, Venus, Earth, and Mars. Now, because they are fairly toward the center where it's very hot, they are made of, we say, rocky planets because they're made of elements that have a higher melting point and still could survive that heat closer on. Farther out, you have more gaseous planets, Jupiter through Neptune, and they formed are called the gaseous giants because they have elements that have a lower melting point, and so they tend to be gases. Now, keep in mind, once again, some of them so far from the sun that they're low enough temperatures that they can actually be liquids, or possibly because of the force of gravity pulling them together in the center, even solid. We think hydrogen may be a solid in the core of Jupiter. Okay, but that's now, since this whole thing was spinning one direction, There's a couple things that this theory explains, and that's why we think it's correct. Obviously, like I said, no one was there. But the point is that it, one, explains why we have this orderly motion of the planets around the sun because they were all part of the spinning mass. And since they were all part of the same mass, now, if here's the sun, all these planets are spread way out, but they all pretty much go on the same elliptical plane or flat plane that they would all hit in. Okay? All right. And so the nebular theory explains why they are all pretty much on the same elliptic or plane that they circulate on. It also explains why the inner ones were more rocky because it was hotter and therefore uh, it's made primarily of materials of higher melting point. And then the Gassian or Jovian planets, gaseous giants, are made of things that have lower um, melting points. And so that kind of explains that, which is kind of handy. Anytime a theory explains things, once again, do we know if that's 100% correct? No, we weren't there, but it does explain things that fits with what we do see. And so we keep that theory. All right, so let's start with our theory of the solar system. We're going to start with the sun. All right, and because remember, once again, the sun is a star. Okay, sometimes we forget that because we see it all day long. We can't see other stars because our star is so bright. But keep in mind is, all right, starting in the middle, we'll start at the core. Good name for it. Everything seems to be called the core in the center. Not called nucleus, a core. Okay, but the core is where the fusion happens. It's where gravity is the strongest, and gravity is what forces the fusion of hydrogen atoms. There's such high gravitational forces, it basically uses the gravitational force to squeeze them together and make helium. Okay, and for every second, scientists estimate there are about 657 million tons of hydrogen, and they're being changed into 653 million tons of helium. But something, whoa, 657, we only end up with 653. What happens? Those 4 million tons. Well, those 4 million tons of matter are being changed directly into energy using Einstein's E equals mc squared. Um, and so enormous amounts of energy are being released, okay? And usually as radiant energy, we say radiant because it's being sent out in rays from the sun in all directions. Keep in mind, we only get what comes our direction, so we're only getting a small segment of the amount of energy that's being discharged. But in the core, the temperatures are somewhere around 15 million Kelvin. Obviously, once again, we've estimated. We have stuck a thermometer there and checked it, okay? And it is so dense from the extreme uh, how big the sun is and all the force of gravity pushing down. It's at the center of the core is actually 13 times denser than lead, okay, which is extremely dense metal here on Earth, and so it is very, very intense there. Okay, the energy from there, from the core, goes out. When it hits the surface, there are gases there of the sun, and when it interacts, the energy interacts with those gases. That is where it emits the electromagnetic waves that we know as infrared, light, radio waves, X-rays, all the different types of radiation that can come out from there, including visible light that we actually see. Okay, so that is the core, and that's where all that happens. Next layer is the photosphere. Okay, photo means light. It's a surface of the sun, we would say. It's only about 5,800 degrees Kelvin, which would crispy fry us in seconds, I'm sure, but still, it's about 50 kilometers deep. Okay, this is where we find sunspots. Sunspots, there are some patterns between sunspots which can cause different things here on Earth. Uh, Problems with their magnetic fields that block these hot gases from rising to the surface. Um, and sunspots are only about 4,000 instead of 5,000 something, almost 6,000 Kelvin. And so they're actually little cool spots on there, and they look dark. Uh, some of them may be about twice the size of Earth. So they don't look very big on the sun, but they are very big. And they tend to come and go. They last for a few weeks. Sometimes there'll be clusters of them together, and they can affect radio transmissions and the amount of solar winds given off and things like that on the from the sun. But other than that, um, they don't cause a whole lot of problems. But that's what they are. They're actually cooler spots on the sun's surface. Okay, we're going to stop right there and go to our second lecture, and we invite you to come back and join us there.